So to minimize packaging costs, need to minimize surface area. Now, how do you express the surface area? So I need to find the area of this side. What's the area of this square base? It's a square. Each side is x. So what's the area of a square whose side lengths are all x?
X squared.
X squared. So that's the area of the square base. How about the area of these other sides? What's the area of one of them?
It's gonna be x times h.
X times h. And then what's going to be the other one here?
X times h. So is
And
it gonna be
so we
2?
have 4 of them, right?
4.
Yeah.
We're going to add 4xh. Now the top is open. There's nothing here. So we only have 5 sides to worry about. And this is the area that I want to minimize. This is what I want to minimize. Now, what's the issue? The function that I have that I want to minimize has x's and h's together. I only want my function to have one variable, not two. So what am I supposed to do? Anyone? I want to get h. I don't want this function to be x and h. I want just this function to depend upon x. So I have to use my condition to do something. And what is that something? Okay, let me ask. What's easier to solve for in this condition? Is it easier to solve for x, get x by itself, or get h by itself?
H.
H. So let's solve for h. So from our condition, what is h?
Well, you gotta divide x squared by both sides.
That's right. And I get 94 over
X squared.
x squared.
And you replace that for h and the volume formula.
That's
Yeah,
right.
yeah.
That's right. So surface area equals x squared plus 4x multiplied by 94 over x squared. And then the x's here will cancel out, and I'm left with that the surface area equals x squared plus 4 times 94 is 376 over x. Is this
Did you do
correct?
that? Did you do that in your head?
Yeah.
It's fast. Oh,
It's not that bad. Don't make it seem like I did some craziness. It's not that bad. There's a mathematician. His name is Arthur Benjamin, and he teaches at where does he teach at? I forgot the name. It's a very good school in the on the West Coast, Harvey Mudd, Harvey Mudd College. It's one of Harvey Mudd College is one of the best institutions for undergraduate mathematics. And he actually was at Queens College when I was a student there. And he had like a performance in front of elementary school students at the one of the auditoriums. I forgot the auditorium. I think it's Left Rec uh, auditorium. And you would randomly just he would ask, give me a three-digit number here, give me a three-digit number there, and he would multiply them in a span of seconds. Like he would just do it. I don't know how he would do it, but this is not too bad. 4 times 4 is 6, so that's why I have the 6 here. I carry the 1. 4 times 9 is 36, plus 1 is 37. So
Yeah,
that's
that wasn't too bad. But you said it like like that. That's the same way that I do it. But I'm just saying, like
yeah,
you just said, 9 times
94 times
four
4,
times.
and then I'm like, oh, it's 3090, 376.
Yeah, you said it pretty instantly.
Well, I'm glad I was able to entertain you with my calculation. But yeah, Arthur Benjamin, you actually Google him, and he has a lot of these things online. I think he also has like a TED Talk where he does this. So he's very famous for this. He just like computes big numbers quickly in his head, and he does like this like dramatic, like oh my goodness, what is that 3 times, and then he just gives it to you like some magical. He calls himself a mathemagician. But anyway, that's neither here nor there. So now I have my function that I want to minimize in terms of x. So I did it. So once I have this, what's the next step? Again, this is the hardest part to get to. Once I get this, I should be able to go be systematic about it. So once I have my function, what's the next step? That's right, Coco. Take the derivative. We take the derivative. So I take my derivative and I get 2x. And then what's the derivative of 376 over x? What's the way we should consider this? We should consider this as 376 x to the negative 1 power. Then I apply the power rule, and this will become negative 376 x to the negative 2 power, which can be placed in the denominator as x squared. Are we all in agreement? This is my derivative. And once I find my derivative, I set it equal to 0. And I set it equal to 0 because I'm trying to find the critical numbers, which are the x values that make my derivative equal to 0. And that indicates that it's a relative extrema, whether it be a max or a min. So once I have this, I can solve it, and I get 2x equals 376 over x squared, right? I move the 376 over x squared to the right side of the equation. So I add this on both sides, and I get this. And I'm trying to solve for x, so I'm going to multiply both sides by x squared, and I'm left with 2x cubed equals 376. So then divide by 2. And Andrew, what do I get? Your quick calculations. What's 376 divided by 2?
188.
188. See, you can calculate quickly too. So now x cubed equals 188. So then what does x equal? How do we find x if we know that x cubed equals 188?
You have to take the cube root of both sides.
Correct. So this is the cube root of 188. And that would be what? So the cube root it's 5.72. 5.72.
How did you get that?
I magically found it. I computed it.
Did you plug it into the calculator?
Yeah, of course. I could not do this in my head.
Okay.
Yeah, I did not do this in my head. The cube root of 188. Is
How did you set that up on the calculator? How do you take the cube root?
it depends on what calculator you have. Do you have a TI-84?
Yeah.
Yeah, so I think on the TI-84, you can go to the math, go math,
Hmm.
and I think one of the first few options has a 3 and a square root with it. Do you guys see it?
Yes.
Yeah. So once you include that, once you get that, you can just plug in.
Great. Okay. Thank you.
Mhm. So what does x represent? X represents the length. And then x also is the width. Right? And let me just see. Yeah, so they round it. They round it to the nearest hundredth. So 5.728. This rounds up to 5.73. So it's actually 5.73. 5.73. And then what would be the height? How would I figure out the height if I know what the x value is?
Plug it in, right?
Plug it in. So plug it in where? Plug it in where you have height in terms of x.
Yeah. The first, so
Mhm.
X.
Or you could just plug it in here. I know that the height is 94 divided by whatever the x value is squared. So I know the x value is 5.73. So then I can plug it in. And I get 5.73 squared and divide 94 by that. And I get 94 divided by 5.73 squared. And I get 2.862, which I can round to 2.86. So this is my answer for the height. And this is my answer for the base. So 286. 2.86 inches. Does that make sense? Edwina, does that make sense?
Yes, it makes sense.
Okay, good.
Thank you.
So any other questions about the homework? So if not, let's continue with what we were doing last time. We're finding the derivatives of exponential and logarithmic functions. So just to recap really quickly, what are the derivatives of exponential functions? So what's the derivative of e to the x?
It is e to the x.
It's e to the x. It's the same. It doesn't change. Very special. And then what's the derivative of ln of x? It's a little weird. This is a weirder one.
I think
1 over x.
yeah.
That's right. 1 over x. So what would be the derivative of the following? What would be the derivative of this function? So if I gave you f of x is equal to 4e to the 3x plus 2, what would be f prime of x? Is that too much? What differentiation rule would we have to apply to figure out the derivative?
The
Chain.
chain rule.
I would have to use the chain rule.
Yeah.
So what does the chain rule state? Take the derivative of the
Of
outer
the outer
function and
and the inner.
multiply it by the derivative of the inner. So what's the derivative of the outer function? It's 4 times e to something. But what do we know? E raised to something equals e raised to that same thing. So it doesn't change. So then the derivative would be what? 4e to the same thing, correct? But what's the issue? There's a inner function, and my inner function is in the exponent. So what's the derivative of 3x plus 2?
3.
3.
3. So I multiply by 3. And so then my final answer for my derivative is
12.
12e raised to the 3x plus 2, because I multiply 4 and the 3. And that would be my final answer.
It's not too bad.
It's not. Hopefully not. But again, if you have any questions, just let me know. Okay. So how about
Professor, are we just going over like last week's class? Can you go over expanding logs after this one, I guess?
yeah, sure.
Yeah, thank you.
Um let me give you another one. How about like this? If I have my function 3e to the negative 1x, 1 over x, what is my derivative?
Are you gonna rewrite it like upside down?
No,
Oh, you keep it the same?
I keep it the same. So it's
Time.
3e to the negative 1 over x, but I need to include what?
The inner
Oh,
Of
inner
the
function.
I need to multiply by the inner function, and my inner function in this case is whatever the exponent is. So what's the derivative? So I'm just going to write this a little more explicitly. What's the derivative of negative 1 over x?
1 over x squared.
Perfect. This is 3 times e to the negative 1 over x times 1 over x squared. Perfect. And then I can rewrite this if I'd like into more compactly. 3 times e to the negative 1 over x squared. Okay? Does that make sense? The chain rule and the differentiation rule for e functions with the base e.
yeah.
Yeah.
Okay. So now let's look at logarithmic functions a bit. So let's say I want to differentiate the function 3x squared times ln of x. pardon me, ln of 2x, what would be the derivative? So what rule should I apply? What differentiation rule should I apply?
Product.
Product. So the product rule states derivative of 1, leave the second alone, plus leave the first alone, derivative of the second. So the derivative of the first,
6x.
6x. So it'd be 6x times ln of 2x, leave that alone, plus 3x squared times the derivative of ln 2x. So what's the derivative? Let me just write this on the outside here. The derivative of ln 2x. What is this derivative?
1 over 2x.
1 over 2x. You're missing something. Do you see I have an outer function and an inner function? So my outer function is ln. The derivative of ln is 1 over whatever is inside. But then I need to multiply the derivative of the inside,
2.
2. And the 2's cancel, and I'm left with 1 over x. So really, what pops out is a 1 over x. The x's cancel here. So my final answer is 6x times ln of 2x plus 3x. And I am done with this. So all the differentiation rules that we've discussed, the product, the quotient, the chain rule, they always will come back. But now we're including this new differentiation rules for exponential functions and for logarithmic functions. Okay, and let's do one more of these. What if I have something like this? What if my function is ln of x minus 2 and this thing is cubed? What would be the derivative? Okay, so I'm gonna try to kill two birds with one stone. So what do I know about the inside of the logarithmic function? I have x minus 2 and that thing is cubed. What properties do I know of about logs?
Chain. Oh, not logs.
You mean the power rule? Because I have a power inside my logarithmic function.
Does that
So
mean
remember-
that you can bring the 3 in front of the ln?
Correct. So I can actually rewrite this as 3 times ln of x minus 2. Isn't this a bit more simpler
Yeah.
to differentiate? And how do I differentiate?
And then if you take the derivative, would you also just take the derivative of 3?
I don't need to
And
take
then-
the derivative of 3 because this is like a constant. This is a
Oh, it's like
constant.
it's outside of the
Yeah,
derivative. Okay.
it's
I
being
understand.
multiplied to the function. So actually the 3 just will survive the differentiation. It just goes along for the right.
So
then what would-
ln1?
No, what would be the derivative of ln? It's 1 over
1 over
whatever's inside.
2.
So it's 1 over x minus 2. Then I would have to multiply by the derivative of x minus 2 but that's just 1. So my derivative is simply 3 over x minus 2. I could have done it differently though. This is one way of doing it, by using the powers of logs. The other way would be to straight up just differentiate this. But if I do it just straight up, this would be 1 over x minus 2 cubed, and then I would multiply by the derivative of the inside function, which is x minus 2 cubed. So what's the derivative of x minus 2 cubed? Using the chain rule, it would be 3 times x minus 2 squared. Do you guys see that?
Mhm.
And then what happens? The x minus 2 cancels. And what do I get at the end?
3 top.
3 over x minus 2, which is exactly what I got the first time. But do you see how the first way that we did it was simpler? Because we utilized the rules for logs. Whereas here, we didn't even consider doing that, and we just straight up had to do the chain rule, which is also not that bad, but there's more involvement of differentiation rules, where here it's just straight. We just straight differentiate once. We don't have to do it twice, as is accustomed in applying the chain rule.
For some reason, I feel more comfortable with the second one.
Really?
That's
So you don't.
because it applies to all of them. Like I don't have to think of a shortcut. Like it just applies.
You just don't think. You're just a robot that performs chain rule, chain rule, chain rule, right?
Yeah, yeah.
Well, it's, different strokes for different folks, right? Some people want to think it out so they don't have to do so much computation, and other people don't mind because they want to not think, so then they just want to do.
It's more
And
like
perform.
systematic.
It's
you
more
know?
systematic. I
Yeah.
agree. If you like the systematic nature of differentiating, then you're not going to really care about that. But if you want to be slick, a little slickster, right? You want to avoid using computation, which tends to be what mathematicians avoid. They don't like doing computation. Like they like to find a way to minimize computation while getting the same answer.
Ironically.
Ironic.
Crazy.
Yeah. So we go with this?
Yep.
Okay. So I guess the last thing.
That's everything.
What else do you want?
Well, I thought there was more to it, but if
There's
that's
more to
it,
what? There's more
to
to the class or more to
no,
this?
to the derivative, the differentiating of uh logarithm if
Logarithmic functions. So in terms of, is there anything else beyond this in terms
our
of,
for
huh?
calculus 1.
No, like these problems can get more difficult in terms of the logarithmic nature of it. I can give you problems that are more difficult, but in terms of what else are we going to be doing, that's the extent of it for this class in terms of differentiating logarithmic functions. That's it.
Oh, but it could get more complicated.
Oh, of course. Oh, this
Yeah.
is easy. Easy.
Could always get more
We
complicated.
can just start adding more x's and then squaring and then to the fifth and then divided by the cube root.
To the
Like we
fifth?
can, yeah, we can do anything we'd like. I can make things up as I speak.
Bring cosine and
Yeah, so if you notice throughout this whole course, we have not touched trig.
Thank God.
And trig is an essential part of calculus. So we did not stress trig. We stressed polynomials, we stressed rational functions, and we just discussed exponential and logarithmic functions. because they tend to be more on the financial side of things, on the business economic side of things.
I love
Whereas
it.
trig is more on the physics of things side. But that's
Professor, we're gonna
another
have a
uh-huh.
review day like before Monday, right? Like you said, you're gonna have.
Correct.
Yeah.
I think that's the whole reason I'm doing so much better in this class than the first time I took calc, because that
Because
had a
there's
lot
no
of
trig.
cosines. Yeah.
Yeah. So normally in a just like a standard calculus course, it would always include trig. So you would know the derivatives of sine, cosine, and tangent, and you can go crazy with that.
Yeah, I was lost. And then the professor, his native language was in English, so
Got it.
that didn't help either.
That's a common occurrence. It's a common occurrence in mathematics courses, especially as you get into higher up and more advanced courses. It tends to be that way, but not always. But it tends to be that way. Okay. So I'm going to present something that I think most of you, I assume, um, already know, given the context of your backgrounds. So this is like, I guess, the final thing, compound interest.
Hmm.
I'm pretty sure everyone has some exposure to this, correct?
Yep.
Yeah, those are fun.
Those are
That's how you make a lot of money.
let me share with you a quote from Einstein about compound interest. Have you guys heard of Einstein's quote on compound interest?
No, I would love to hear.
There again.
I would love to hear the quote.
So this is what he says. Let me see if
Compound
I get this
interest is
right.
the greatest thing on earth.
What does he say?
Isn't it say something about like a snowball effect with compound interest that you can make a lot of money? I forgot.
That is the that is that is how most people use compound interest. Like it's like if you invest at age 25 until you're 65 with compound interest, it'll blow up exponentially.
Yeah.
Like,
And
hey,
just
that's where the
one roll.
the whole exponential function
Growth.
comes into play.
Hmm.
Oh,
You
that
want
makes
exponential growth, right? Exponential growth is a very rapid growth. And of course, you want that with your money because you want your money to grow as fast as possible. Um, let me share with you my screen. This is a whole bunch of these images. But what I want to stress is this: compound interest is the eighth wonder of the world. He who understands, he or she who understands it, earns it. He who doesn't, pays it. And that is a quote from Albert Einstein. And you see, Albert Einstein is known for his physics contributions, but he also understood the money aspect of things.
The guy sounds like a smart man.
I mean, obviously, he obviously was. But the thing is, the way I interpret it is also more than just money. When we talk about compound interest, immediately you think about money, correct? But you can also, I believe, apply it to other realms, not necessarily just with money. And that's with anything. Anything that you give your time to, right? Because compound interest is inextricably related to time. And so that's what Andrew was saying. If you start investing at 25, after 40 years, as you know, the market goes the way it goes and the percentages work, and then if you invest a certain amount of money with a certain interest rate over a long period of time, whoop, your money goes up, right? But you can apply this also to other things. Um, the way I apply it is to like, how do you develop an ability or a skill with of some sort? You have to apply time, and the more you apply it, after 10 years, it's amazing at the progress you're able to undergo. So I don't know
Mhm.
if that's what he was also considering, not just the money aspect, just in general. That's why he doesn't talk about money. He just says he who understands compound interest earns it, and he who doesn't pays it. Anyways,
It's like um one of my other favorite quotes that was said, um, but this was by a rapper. But they pretty much said Rome wasn't built in one day, but if you don't do anything today, it won't be built in a year either.
who's this rapper that you speak of?
Nav,
Nav. I've heard of Nav.
yeah, he's from Canada.
Yeah, I've heard of Nav. So is that the rhyme?
Nah, he actually like posted as a
Did
little
it?
quote thing,
Oh, I got it.
and it's like
So yeah,
I
so
feel
Rome
like it's
wasn't built in.
related to it.
Mhm. That's right, and it's also like a journey of 1,000 steps starts with one. That type of deal, right? So once you get the ball rolling,
Yep.
in the beginning is kind of slow, but if you're consistent with it and you keep at it, the interesting thing will be what happens if you were to do that. Like what happens if you dedicate to something over a long period of time? What would be the result? You never know.
Mhm.
So it's not just with money. But anyways, money is the interesting thing. So if I compound interest, what is the formula? Do you guys remember? So A is normally known as my accumulated value, correct?
Mhm.
And then what follows? The principal plus, yeah, the principal amount, which is P, times 1 plus 1 plus what? It's rate times raised to the t, right? Which is time. But with compound interest, it's going to be rate over n to the nt. What is r? R is the annual interest rate. And what is the n? N is the number of periods for compound interest in a year. And t represents the time of investment. And p represents the principal amount. And this is the formula. And what's going to be important to know is certain vocab. So vocab for compound interest. So if I say, if I compound, if my interest is compounded annually, then my end value is 1. So I would have simple interest, right? P times 1 plus r raised to the t power, where this becomes 1, is the simple kind. But then I can have compound interest occurring semi-annually. So what's the end value going to be? 2. That's right. And then we go on and so forth, right? How else can we divide up a year? Well, semi-annually, how else can we divide it up?
Quarterly.
Quarterly. There we go. So n equals 4 because I divided my year into 4 periods. And then at the quarterly, can we divide it even more? Instead of 4 times a year, we can compound it
Monthly?
monthly. So my n value is 12. Well, can I divide it more? Can I divide my year into finer periods?
Yeah, weekly and then days.
There we go. So weekly, so there's 52. Daily, On a non-leap year, it's 365. And we can continue, right? We can do it per hour or no, technically, I mean,
Well, it's a lot of
theoretically speaking,
payments.
right? We can do this per hour. We can also do this per second. And if you really want to be ambitious, you could do it at every waking moment. Do you guys know about that?
Yeah.
What is that called? Compound.
No, I forget. It's like today.
24/7, 365.
No, there's like a name for it.
Every instant. You can compound continuously. Have you guys heard of compound interest continuously?
Yeah,
I've never heard of that before.
it just keeps going and keeps going.
Yes. This formula is PE to the RT. That's where E pops up.
Oh yeah.
Pert. But E pops up. So the story goes like this. This is the story of how people introduced this E. What is E again? We talked about it, right? This is Euler's constant. This is
Mhm.
based upon a mathematician that was around the 1700s. His name is Leonhard. I don't even know how to say it. Euler. Some German guy. But he's not just any German guy. He's one of the greatest mathematicians to ever live. And he found or discovered this constant 2.71a da 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 goes on forever. So the story goes like this. Let's suppose you have $1 and you want to invest this $1 into a bank whose annual interest rate is 100%. So that means after the year goes by, that dollar becomes what?
$2.
$2. But then we say, let's compound the interest twice a year. So then how much is that dollar going to be? So we could do that. So one, that's my principal amount, right? P is 1.
Professor,
And
this is gonna be on the final?
compound interest?
Yeah.
Yes.
Okay.
But all I'm trying to explain is where this E comes from.
hmm
So it comes from the fact that I take one, the story goes, you take $1, invest it into a bank that has an annual interest rate of 100%. So if that's the case, then R it would equal 1, right? This is 100%. You always convert it to a decimal, which is 1. And after 1 year, if you compound it once a year, you would get $2. So this is annual. This is just compound interest annually, right? But what if I want to do it semi-annually? What would be my new accumulated value? So 1 plus 1/2 squared. What is it? Bless you.
Thank you.
What's 1.5 squared? $2 and
25 cents.
25 cents. So that's if my compound interest, if my interest is compounded semi-annually. What if my 100% interest is compounded monthly, for example? What would be the formula? How would it differ? So it would be still 1 plus 1 over 12 raised to the 12 power. Can anybody tell me what I get for this?
2.613.
2.61. So I'm doing better, right? So if I compound my interest, my interest is compounded once, I only double. If my interest is compounded semi-annually, I make 25 extra cents. If I do it monthly, I get to $2.61. And then what should I do next?
Weekly.
Let's just do weekly. So 1 over 52 raised to the 52nd power. So if I compound my interest every week, that dollar becomes how much?
2.69.
2.69. Okay, so I'm still growing, right? So what if I do this every day? Daily. What would be the result?
2.71.
2.71. Now, what if we do it 100,000 times a year?
What do you mean 100,000? Like, is that the continuously version?
Not yet. But let's just suppose I divide my year into 100,000 equal time intervals, which is possible. What if what if I compound my interest? My interest is compounded 100,000 times a year. What does that dollar become?
Oh, it it's 2.71. So does that mean
Ah.
that it approaches
Yes.
a limit?
Thank you, Andrew.
Yeah.
Thank you. That is correct. There's a certain limit to this. It's not infinite. So actually, if I let n, so let's look at this. This is amazing, isn't it? Take the limit, take n and make it go to infinity of 1 plus 1 over n raised to the n. Because that's what's really changing, right? It's just the n, which represents the number of times that the interest is compounded. Make that number infinite. And you know what the limit is?
2.71.
E.
Oh,
No way.
Yeah.
That's freaking crazy, man.
That is crazy.
Smart man.
And that's why you have PERT. That's why you have PE to the RT. It's because the limit is because the original formula that we have, this limit here becomes E as n goes to infinity. You can make a rap song out of this, right? Right, Vitali? You should tell Nav. Nav, make a song about E, compound interest.
Hmm.
So that's where E comes up. And E, this number doesn't only come up in the money aspect of things. It also appears in nature. The way certain population grows, E comes up. The way temperature either something heats up or cools down, E pops up. So that's why
So
E is so special.
so in the rise of COVID cases, would E pop up? Ah.
Why do you think they talk about, oh, this is doubling, this is an exponential? Bacteria, viruses, they double or they reproduce quite quickly in an exponential way. And so that's why when they talk about what did they say? Flattening the curve. They're talking about let's try to not make this exponential. Let's try to like dampen it by the social distancing measures. Because if we don't, this will cover the whole world. And then life as we know it doesn't exist. Yeah, understanding exponent. That's what it says. Compound interest is the eighth wonder of the world. He who understands it earns it. He who doesn't pays it. So if we don't understand how exponential functions work, we're gonna pay for it, whether it be by money or by other measures. So all of this stuff fits. All of it.
Professor, I like how you gave us the background to the E. Like it's pretty cool.
Oh, I'm glad. I'm glad you liked it because also when I came across this, I was like, wow, this is amazing. Because your I guess my original thought was that if I were to compound interest more and more, my dollar would grow without bounds, right? I would make as much as I like, but there's actually a limit behind this structure. So it's not an infinite amount. I thought that I could make from $1 if I apply the interest rate of 100% as many times as I like in a year, then I would get way more than $2. But the max is $2.71. That's as much as I can make, which is not bad. It's almost three times as much, right?
Well, 100% interest rate is amazing.
Right.
That's why
It is amazing, right?
5 times every
But
month.
this is what we do sometimes in mathematics. We suppose, like if we get bounded by the way the world works, then we would never come up with this. But someone say, you know what? Let's just make believe we can make this bank, or this bank exists, which doesn't, obviously. But let's say this bank has this interest rate. What would happen? So these are like thought experiments, and then this is where we these have these interesting results. All right. Okay, so let me just do one last problem and we'll call it a semester. How about that?
Sounds wonderful.
Okay. So it says just one question. How long will it take?
Wait, Professor, don't we have a quiz today?
Yes, we do.
Oh.
We have
Oh
yeah.
no.
Oh, we do. So this, I'm saying this is the last thing.
I don't think he was gonna forget.
I don't think he's gonna forget either. But I can dream.
How long will it take for an investment of $7,000 to double if the interest rate is 8% per year, compounded monthly? So again, I'm going to use the compound interest formula, just a regular one, not the compound continuously, because it's compounded monthly. So I need to recognize what A, P, R, N, and T is. So correct, Coco. The accumulated value would have to be double 7,000. So then A would have to be 14,000, correct? Because that's double 7,000. P is 7,000. R is, what's R? If my interest rate is 8%, what's R gonna be?
0.08.
0.08. Good. And then what is N? Number of times that's compounded, the interest. N is 12. Now what are we looking for? T. T is what we don't know because we're asked how long will it take? So what is T? So then we plug it in and we get 4,000, 14,000 equals 7,000 times 1 plus 0.08 over 12 raised to the 12t. And what am I looking for?
T.
T. Okay. So the first thing I could do is divide by 7,000 on both sides. That just minimizes our computation because I get a 2 on the left side and I get 1 plus 0.08 divided by 12. So I'm going to take this as 1 plus 0.08 divided by 12 and I get 1.006 repeated. So 1.006 repeated 12t.
We wouldn't just round it up. You have to keep it as repeated.
I'm going to keep it as exact as possible.
Hmm.
Now, what's the next thing we have to do? The problem is t is an exponent, but I want to solve
Oh,
for t.
are you going to use try to use like logs to?
Correct. Correct. That's all it is. Use logs. So whenever you have a variable as an exponent, the way we solve for that variable is applying logs. Because if I apply logs on both sides, what can I do with the power?
You can just set them equal to each other.
Not yet. The power, remember by the power rule,
It goes
goes
in
in
front.
front. So this is 12t times ln of 1.06 1.006 repeated.
Mm-hmm.
And now what am I looking for again?
T.
T. So I need to get rid of everything that's next to t. So divide by 12, divide by ln 0.06 repeated of 1.06 repeated. The 12s cancel. And what does t equal? Ln of 2 divided by 12 times ln of 1.06 repeated.
Professor,
Yeah.
is there a particular reason why you used ln instead of just like log?
Because remember, there's two kinds of logarithms that we tend to use. We either
Mhm.
use the log base 10 or
Yeah,
log
that's.
base e.
I assumed you were gonna use log base 10, but you used ln. So like, is there a
It
reason why?
doesn't matter at the end
Oh,
of the
okay.
day. I can
All
use log base 10 and it would look just like this. It would look
Okay.
like t equals log of 2 divided by 12 times log 1.06 repeated. And the cool thing is, whether I compute this expression or this expression, I get the same thing. It doesn't really matter. So I'm just accustomed to using ln. So ln of 12, 2. ln of 2 divided by, let me use the fractions. So ln of 2 divided by 12 times ln of 1.006. And I'm gonna approximate with this. So this is 9.65 dot dot dot. So in roughly 9.5, 9.6 years, that's how long it would take. And look, just to show you, if I use log base 10 and I do that instead, 12 times log base of 12. Sorry, it should be 2. What am I doing?
The bottom should be 1.006.
That's right, 1.006. You see, I get the same thing.
Okay.
So it doesn't matter what log base you use, as long as you use log, you should be good.
Mm.
So it would take this investment at a interest rate of 8% being compounded monthly. It would take it 9.65 years in order for that investment to double.
Hmm.
And this whole idea of compound interest is like the ABCs of financial mathematics. If you want to get into financial mathematics side of things, if those of you that might be interested in actuarial science, there's a whole financial mathematical aspect. And this is like the first thing you master. And then there's a whole bunch of other things like annuities and present value of money and this, that, and the third. Okay. Any questions?
No.